So let's do the second part of this paper, nice paper on Pacific decadal scale variability. As opposed to Pacific decadal variability, they are saying Pacific decadal scale variability. So there are multiple modes, as we already saw, and we just looked at this nice figure which showed how the mean circulation and the atmospheric and oceanic modes look like in the North Pacific and the South Pacific. Continuing with that, where do you get these modes from? Of course, one fundamental model used to explain oceanic reddening was first introduced by Hasselmann in 1976 in a one-dimensional equation. You may already know that Hasselmann was part of the three-member team that won the Nobel Prize for Physics recently, Suki Manabe, and the third Hasselmann, and the third person was somebody who did some related symmetrical work or something that you can look up. The equation looks, really disarmingly simple, as they say. Dot dt, O is a variable as a function of time, is equal to alpha times A as a function of t minus O itself divided by some decay time scale of tau. So here the rate of change of the anomalies of an oceanic variable O on the left hand side is driven by atmospheric anomalies scaled by a conversion factor alpha, and where the oceanic anomaly exponentially decays with the time scale of tau, representing the memory of the oceanic variable being considered, whether it's heat content or sea surface temperature and so on. When discretized into a difference equation, this model is equivalent to an autoregressive model of order 1, so AR1, which is a known low frequency filter. If you don't know what autoregressive model is, you can look it up. Using this simple model, one can reconstruct the time series of the Pacific decadal oscillation, the North Pacific gyre oscillation, South Pacific decadal oscillation by simply forcing equation 1 with the atmospheric time series of the Aleutian low, North Pacific oscillation, and the South Pacific oscillation modes respectively, and using decadal, decay time scales of 8 to 12 months, which is the typical decay rate of SSTA in the extratropics. By correlating the output of equation 1 with basin scale SSTA, we recover the global footprints of the PDV modes. So that's what we looked at here. And moving forward, what are the dynamical modes of Pacific decadal scale variability? I hope the sound is still okay. While the statistical modes of PDV provide a useful description of a Pacific low-frequency climate variability and are routinely used to identify and predict how climate variability impacts biogeochemical cycles, marine ecosystems, weather and climate extremes, the objective of this review is to identify and understand the physical mechanisms of the dynamical modes of Pacific climate variability. Marine ecosystems and biogeochemical cycles are important because the original idea of a decadal variability or a regime shift in the North Pacific came from biological data. I think it was a zooplankton data from and fisheries data from the Japanese, where they found a regime shift in the 1970s, 1976, I think, and then the climate people noticed it, and then they have been trying to build a story of these regime shifts, and that it's there in the tropics as well. And we still don't have complete understanding of the mechanisms, which is what we are discussing here. The computation of climate modes through EOFs imposes an orthogonality constraint in spatial patterns and temporal evolution of the modes. Empirical orthogonal functions by name itself, mode 1 is supposed to be orthogonal to mode 2 and so on. However, as noted above, in the low frequency regime, these modes converge to a similar pattern of variability, so they can all look like ENSO-like with broader or narrower meridional patterns, and are spatially non-orthogonal outside the geographical regions where the modes are defined. So you can see the similarity of PDO and SPDO here. So that's the PDO signature here and the SPDO signature. So the meridional scale is different, but they look very similar, even though this one is focused on the South Pacific, but outside of that they can be similar, and that's the idea being discussed here in terms of orthogonality. Uh, the findings, this finding, indicates that the orthogonality constraint is an artifact of the definition and not a physical constraint. Moreover, eigenmodes of physical dynamical systems are typically not orthogonal due to asymmetries both in space, such as the differing regions of strong or weak gradients, and between variables, such as when one variable appears in the tendency equation of a second variable but not vice versa. So there are asymmetries in that sense. In fact, strong evidence exists that the modes obtained with the statistical approaches such as ENSO, the PDO, and ENSO and PDO result from the constructive superposition of several non-orthogonal dynamical modes. Unfortunately, computing the dynamical modes of the Pacific climate system is non-trivial and relies on our ability to perform an eigenmode analysis of the true dynamical operator controlling the evolution of this system. While a full knowledge of such an operator is hard to obtain apart from very simplified physical models, it's possible to use empirical approaches to approximate this operator from observations in an inverse sense and determine its eigenmodes. Here we use one such empirical dynamical model of the Pacific SSTA to examine the spatial and temporal variability of observed dynamical modes. Okay, so I'm not going to go into the details of the models, but it's worth reading if you want to follow up. So here we are looking at the warming trend mode, which is basically a linear trend, and we already talked about the hotspots here when we talked about the tropical Pacific decadal variability. We have the PDV modes given as the Kuroshio-Oishio extension mode and the North and Central Pacific modes with different loadings and different time series. As you can see, the trend of course is going upward, and it is upward throughout the time series from 1900 to 2019 or 2017 or so. And you can see that the Kuroshio-Oishio extension has different type of time scale compared to the NPCP mode here, and these are the ENSO modes, the East Pacific ENSO with the warming focused on the Central Eastern Pacific occurring at 3 to 6 years, and the CP ENSO or the Central Pacific ENSO has a loading more towards Central Western Pacific in the deep tropics and has a quasi-biennial time scale. And there are lots of debates about whether they are really independent or they're just something called ENSO diversity. Both seem to have recharge discharge mechanism, for example, and so on and so forth. And you have the ENSO decay mode, which of course is 8-month decay time scale, similar to what we assumed here in the Klaus Hasselmann model, right? So if you do the dynamical filtering of the PDV modes, regression maps of indices of Pacific climate variability with SSTA, with dynamically filtered SSTA for where the KOE and NPCP modes have been removed using the linear inverse model as a dynamical filter. So it's the full IPO mode, TPDV that we already talked about, and the PDO. You can decide for yourself what the differences are, and obviously they are not orthogonal in that sense. And the SPDO mode, as we said, outside the domain of the focus, they are kind of similar. So again, non-orthogonality. If you remove the IPO and PDO, let's see, in this one you have removed. So here KOE and NPCP modes are removed, and what remains, so that's the no PDV modes. And you can see again IPO looks like this, and TPDV looks like this, PDO looks like this, and SPDO looks like this, and now they are looking much more similar except in this region. So the LIM model does ensembles, so basically you do some perturbations and try to see how the different modes are contributing to the Pacific decadal variability, decadal scale variability. So this is an ensemble reconstruction of the PDO from 20 LIM stochastic simulations showing the relative contributions of KOE, NPCP, and EP-ENSO eigenmodes. So basically, we talked about during TPDV whether PDO or TPDV can be just a superposition of El Nino and La Nina, but this would argue that there are more complicated contributions. You have to go and read why ensembles are done. Basically, you want to see what is the natural variability of these superpositions, and you can see that they are large ranges. Sometimes EP-ENSO is large, with most of it coming from NPCP and KOE having no contributions. In other cases, the EP-ENSO has no contribution, but KOE and NPCP are dominating, and so on and so forth. So there are ways to learn that initial conditions, perturbations, or other things can produce different combinations of KOE, NPCP, and EP-ENSO to PDO. So the null hypothesis then for energizing the basin scale tropical symmetric PDV pattern, you have to eventually say where this energy at decadal time scale is coming from. Is it really just integration of stochastic atmospheric forcing, or is it some internal variability where the ocean is moving around heat and producing internal variability to the ocean itself, and so on. So the gray path shows how high frequency stochastic variabilities in the atmosphere influence the ENSO systems. The blue path shows how shows the growing phase of the tropical Pacific decadal variability, which is the sequence of ENSO precursors in the extratropics to ENSO in the tropics. The red path shows the decaying phase of the TPDV, which is the sequence of ENSO in the tropics to ENSO teleconnections to the extratropics. The SSTA map shows the North Pacific and South Pacific regions representing the oceanic expressions of the northern and southern ENSO precursors, respectively, in January to March in panel A and B, and their seasonal progression in January to March +1, so depending on the years. These maps were obtained by correlating so there are some statistical details. So you can see that you have the North Pacific with ENSO in the fall reacting with winter in the +1 year. So because you cross December, January into February, you think about winter +1 year. So there is internal stochastic variability where ENSO and the extratropics and ENSO precursor in the winter to spring can all interact. So North Pacific precursors here and going from tropics to extratropics with internal stochastic variability of the atmosphere doing its thing and ocean doing its thing. So here is the SSTA of January to March. I'm being very brief, but obviously the idea here is to just discuss all the potential interactions like stochastic forcing, so things like WWBs or westerly wind bursts, and also the tropical Atlantic impact, which could be coming through the Walker cell or the ITCZ. So there are many pathways you can do it, basically because the atmospheric bridge has to connect it. You don't have an oceanic tunnel, whereas with the Indian Ocean you would have an oceanic tunnel and the atmospheric bridge and so on. So in the South Pacific again you have ENSO teleconnection in the atmosphere. So SSTA in January to March of the next year, the following year, with internal stochastic atmospheric variability again interacting with the precursor ENSO precursor atmosphere, so ENSO teleconnection, ENSO precursor atmosphere. So South Pacific feeding back to the tropical decadal variability, and here is the SSTA January to March. What do you get out of this? Basically that there are all kinds of feedbacks happening from the tropics to extratropics, and so is a full coupled mode, but is influenced by and influences the other extratropics in both hemispheres. If you look at the mechanisms of NPCP and KOE modes. The NPCP mode here is energized by the two-way coupling dynamics between the tropics and extratropics. That's kind of a broad statement with North Pacific meridional mode kind of pattern there. So mechanisms of NPCP mode, North Pacific, extratropical ENSO precursors, 1 to 2 years. There is also some debate that Central Pacific El Nino is basically a manifestation of the North Pacific meridional mode, and the westerly wind bursts could be part of that as well. Lots of work, lots of ideas, but synthesizing them into one picture, especially for low frequencies, is very tricky. So in the tropics, from the North Pacific, you have NPO and PGO feeding into CP and so, or to EP and so, and back to the Aleutian Low and PDO. So ENSO teleconnections 6 months to 1 year. So you can read the numbers back to what they are all corresponding to. Whereas the mechanisms of the KOE mode, you have the KOE mode is energized by the two-way coupling between the KOE and the Central and Eastern North Pacific and its interaction with the NPCP mode. Okay, the color maps in the top right corner of each panel show spatial expressions of the modes from figure 3 we looked at before, oceanic expressions. So the abbreviations are the same. So you have again North Pacific and the tropics, KOE atmospheric forcing as opposed to extratropical ENSO precursors with 1 to 2 years here. So KOE instead of the NPCP, and you have CP and EP ENSOs feeding the Aleutian Low PDO with 2 to 4 years affecting the KOE. There are Rossby wave ideas and so on. Basically, you can go from North, East, Central Pacific to KOE through Rossby waves as well. So there are the Rossby waves there going from NPO and PGO, and you have a feedback from KOE to NPO and PGO. So everything is feeding back to everything. Does it really help you? Well, please read the paper to see that these ideas are there, but actually deconvolving all of them is not easy. Not enough data, plus models may be doing something similar yet mechanistically different, especially because we don't know the mechanisms anyways, right? So atmospheric response to KOE SSTA in frontal variability in Earth system model ensembles. As I said, high latitude, mid latitude, extratropical AC interactions are tricky because in the tropics, warm SSTs can drive convection and coupling, whereas in the extratropics, it's not always clear, but fronts do produce a response. Panel A and B show the responses of the 300 HPA and precipitation anomalies respectively in high resolution ensemble simulations, and panel C and D show responses in low resolution ensemble simulations. So obviously we are now getting deeper and deeper into trying to understand them with models, and then saying high resolution models produce something and low resolution models produce something else. So high resolution Earth system NPO and ENSO precursor pattern is here as the 300 HPA anomaly. Low resolution Earth system model looks remarkably different, which is always tricky to understand. Local response in the KOE and impacts over North America, which is why we are worrying so much about these things, because they have impacts on land, and decadal variability. So, it's always critical for decision horizons as well, and local response in KOE in the low resolution Earth system models. So do what you want with it, but essentially we don't know the answer and we are still seeking the answer. Average correlation maps of wind stress and SSTA response to KOE forcing index for lags of 12 months and 24 months. Abbreviations, of course, again KOE and so on. And you can see 12-month lag, you get one pattern which has got a wave-like pattern, let's say here, whereas this has got the North Pacific meridional mode kind of pattern. So you can go back and see what these are in the context of the Pacific decadal variability, but basically we are again talking about NPCP mode, KOE mode, their interactions, and the lags that we are talking about in terms of the SSTAs with KOE forcing. So Rossby waves go westward, and then you can have atmospheric response that is bringing it eastward, let's say, and so on. So should I read this off now only? Let's do that in the next podcast, because this one is already fairly long, and I'm being rather brief and not very detailed in terms of the context for the papers. But my main idea is to introduce this to you so you can read. And I like to look at figures, because the figures should be worth 1,000 words, but there are 10,000 words in the paper that you have to understand as well. So I'll let you do that. Let's come back and summarize. Then we'll have a few more points to make on what the paper is all about. And it's the same as TPDV, that we know in the data we see these decadal scale variabilities, and there are multiple atmospheric and oceanic signatures, hemispheric signatures, interhemispheric signatures, tropical and extratropical loadings, and so on. But what are the mechanisms? Everything is interacting with everything, and it's easy to say we don't really know exactly what's happening right now, but somehow there is energy at these low frequencies that it jumps out in the data. Okay, so let's come back and read the summary.